Hello dear students, today we are going to discuss radiation, radioactivity, types of radioactive decay, units of radioactivity and half-life. The objectives of the topic are to understand what's radiation and what are its different types, to gain insight about the harmful effects of radiation, to understand what's radioactivity and what are its units, to know about different types of radioactive decay. Now let's first know about what's radiation. Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium. These include electromagnetic radiation such as heat waves, radio waves, visible light, X-rays and gamma radiations. Particle radiations such as alpha radiations, beta radiation and neutron radiation. Acoustic radiations such as ultrasound and seismic waves. Radiation is often categorized as either ionizing or non-ionizing, depending on the energy of the radiated particles. Ionizing radiation carries energy more than 10 electron volt, which is enough to ionize atoms and molecules and break chemical bonds. A common source of ionizing radiation is radioactive material that emit alpha, beta or gamma radiation, consisting of helium nuclei, electrons or positrons and photons respectively. Other sources include X-rays from medical radiography examinations, gamma rays, X-rays and the higher energy range of UV light constitute the ionizing part of electromagnetic spectrum. The lower energy and the longer wavelength part of the spectrum, including visible light, infrared light, microwaves and radio waves, is non-ionizing. Its main effect when interacting with tissue is heating. This type of radiation only damages cells if the intensity is high enough to cause excessive heating. Ultraviolet radiations have some features of both ionizing and non-ionizing radiations. Now first one, ionizing radiations. Radiations with sufficiently high energy can ionize atoms, that is, it can knock electrons off from atoms and create ions. Ionization occurs when an electron is knocked out of the shell of an atom, which leaves the atom with a net positive charge. Living cells, more importantly the DNA of the cells, can be damaged by this ionization. Exposure to ionizing radiation is considered to increase the risk of cancer. Ionizing radiation has many practical uses in medicine research and construction, but presents a health hazard if used improperly. Exposure to radiation causes damage to living tissue. High dose result in acute radiation syndrome with skin burns, hair loss, internal organ failure and death. Ionizing radiations include, first, UV radiations. Ultraviolet rays of wavelength from 10 nanometer to 125 nanometer ionizes air molecules, causing it to be strongly absorbed by air and by ozone. About 98% of UV rays are absorbed by ozone layer. Ionizing UV rays therefore does not penetrate Earth's atmosphere to a significant degree. The ozone layer starts at about 20 miles and extends upwards. Some of the ultraviolet rays that reach the ground are non-ionizing but are still biologically hazardous as it causes electronic excitation in biological molecules. An example is the formation of pyrimidine dimers in DNA. This property gives the UV spectrum some of the dangers of ionizing radiation in biological systems without actual ionization. In contrast, visible light and longer wavelength electromagnetic radiation such as infrared, microwaves and radio waves consists of photons with too little energy to cause damaging molecular excitation. Now second, X-rays. X-rays are electromagnetic waves with wavelength less than about 10⁻⁹ meter. When an X-ray photon collides with the atom may absorb the energy of the photon and boost an electron to the higher orbital level. Or if the photon is very energetic, it may knock the electron from the atom altogether, causing the atom to ionize. Generally, larger atoms are more likely to absorb an X-ray photon since they have greater energy differences between orbital electrons. Soft tissue in the human body is composed of smaller atoms than the calcium atoms that make up the bone. Hence, there is a contrast in the absorption of X-rays. X-ray machines are specifically designed to take the advantage of the absorption difference between bone and the soft tissue, allowing physicians to examine structure in the human body. Now third, gamma radiation. Gamma radiation consists of photons with a wavelength less than 3 × 10⁻11 meters. Gamma radiation emission is a nuclear process that occurs in an unstable nucleus to get rid of excess energy after most nuclear reactions. Both alpha and beta particles have an electric charge and mass and thus are quite likely to interact with other atoms in their path. Gamma radiation, however, is composed of photons which have neither mass nor electric charge and as a result penetrates much farther through matter than either alpha or beta radiation. Now, alpha radiation. Alpha particles are helium nuclei with 2 protons and 2 neutrons. They interact with matter strongly due to their charges and combined mass. They penetrate a few centimeters of air or a few millimeters of low-density material. Now, beta radiation. Beta minus radiation consists of an energetic electron. It's more penetrating than alpha radiation but less than gamma radiation. Beta radiation from radioactive decay can be stopped with a few centimeters of plastic or few millimeters of metal. It occurs when a neutron decays into a proton in a nucleus, releasing the beta particle and an antineutrino. Beta radiation from LINAC accelerators is far more energetic and penetrating than natural beta radiation. It is sometimes used therapeutically in radiotherapy to treat superficial tumors. Beta plus radiation is the emission of positrons, which are the antimatter form of electrons. When a positron slows to speeds similar to those of electrons in the material, the positron will annihilate an electron, releasing 2 gamma photons. Now, neutron radiation. Neutrons are categorized according to their speed energy. Neutron radiation consists of feed neutrons. The neutrons may be emitted either during spontaneous or induced nuclear fission. Neutrons are rare radiation particles that are produced in large numbers only where chain reaction, fission or fusion reactions are active. Neutrons are the only type of ionizing radiation that can make other objects or materials radioactive. This process called neutron activation and is the primary method used to produce radioactive sources for use in medical, academic and industrial applications. Now second one, non-ionizing radiations. The kinetic energy of particles of non-ionizing radiation is too small to produce charged ions when passing through matter. The effect of non-ionizing forms of radiation on living tissue has only recently been studied. Nevertheless, different biological effects are observed for different types of non-ionizing radiation. First is UV light. The lower part of the ultraviolet spectrum, called soft UV, is non-ionizing. However, the effects of non-ionizing UV light on biological systems exposed to it are such that even this part of UV is often compared with ionizing radiation. Now, visible light. Visible light is a very narrow range of electromagnetic radiation of wavelength that is visible to human eye. More broadly, physicists use the term light to mean electromagnetic radiation of all wavelengths, whether visible or not. Now, infrared light. Infrared light is electromagnetic radiation with wavelength longer than that of visible light, but shorter than that of microwaves. Now, microwaves. Microwaves are electromagnetic waves with wavelength ranging from as short as 1 millimeter to as long as 1 meter, which equates to the frequency range of 300 MHz to 300 GHz. Radio waves. Radio waves are the type of electromagnetic radiation with wavelengths in the electromagnetic spectrum longer than infrared light. Like all other electromagnetic waves, they travel at the speed of light. Naturally occurring radio waves are made by lightning or by certain astronomical objects. Artificially generated radio waves are used for fixed and mobile radio communication, broadcasting, satellite communication, computer networks, and innumerable other applications. Now, thermal radiation or heat. Thermal radiation is the common synonym for infrared radiation emitted by objects at temperatures often encountered on Earth. Thermal radiation refers not only to the radiation itself but also the process by which the surface of an object radiates its thermal energy in the form of black body radiations. Infrared or red radiation from a common household radiator or electric heater is an example of thermal radiation. Now, black body radiation. Black body radiation is an idealized spectrum of radiation emitted by a body that is at uniform temperature. The shape of the spectrum and the total amount of energy emitted by the body is the function of the absolute temperature of that body. Now, radioactivity. Radioactivity refers to the particles which are emitted from nuclei as a result of nuclear instability. The most common types of radiations called alpha, beta, and gamma radiations. But there are several other varieties of radioactive decay. Nuclear radiation occurs in other forms including emission of protons or neutrons or spontaneous fission of a massive nuclei. Of the nuclei found on Earth, the vast majority is stable. This is so because almost all short-lived radioactive nuclei had decayed during the history of the Earth. Now, discovery of radioactivity. Radioactivity was discovered in 1896 by a French scientist, Henri Becquerel. While working on phosphorescent materials, these materials glow in dark after exposure to the light, and he suspected that the glow produced in cathode ray tubes by X-rays might be associated with phosphorescence. He wrapped a photographic plate in a black paper and placed various phosphorescent salts on it. All results were negative until he used uranium salts. The uranium salts caused a blackening of the plate in spite of the plate being wrapped in the black paper. These radiations were given the name Becquerel rays. Marie and Marie Curie, after their research on Becquerel rays, led to the discovery of radium and polonium. They coined the term radioactivity. The study of radioactivity is the important factor in science and medicine. Now, radioactive decay. Radioactive decay, also known as nuclear decay or radioactivity, is the process by which nucleus of an unstable atom loses energy by emitting radiations including alpha particles, beta particles, or gamma rays. A material that spontaneously emits such radiations is considered radioactive. There are many different types of radioactive decay. A decay or loss of energy from a nucleus results when an atom with an initial type of nucleus called the parent nuclide transforms into the daughter nuclide. The transformation produces an atom in the different state. In such decays, the parent and the daughter nuclides are different chemical elements, and thus the decay process results in the creation of an atom of different element. This is called nuclear transmutation. The first decay processes to be discovered were alpha decay, beta decay, and gamma decay. Another type of radioactive decay is called spontaneous fission. Happens when a large unstable nucleus spontaneously splits into two or occasionally three smaller daughter nuclei and generally leads to the emission of gamma rays, neutrons, or other particles from those products. Now, alpha decay. In alpha decay, the nucleus emits a helium nuclei, that is an alpha particle. Alpha decay occurs most often in massive nuclei that has too large proton to neutron ratio. Alpha radiation reduces the ratio of protons to neutrons in the parent nucleus, bringing it to the most stable configuration. In alpha decay, the atomic number changes, so the original atoms and the decay product atoms are different elements and therefore have different chemical properties. Beta decay. Beta particles are electrons or positrons. Beta decay occurs in the nucleus with too many protons or too many neutrons. One of the protons or neutrons is transformed into the other. Beta decay is of two types, beta minus decay, beta plus decay. In beta minus decay, a neutron decays into a proton, an electron, and an antineutrino. In beta plus decay, a proton decays into a neutron, a positron, and a neutrino. Both reactions occur in order to move the product closer to the region of stability. These particular reactions take place because conservation of laws are obeyed. Gamma decay. In gamma decay, a nucleus changes from higher energy state to the lower energy state through the emission of electromagnetic radiations. The number of protons and neutrons in the nucleus does not change in this process, so the parent and the daughter atoms are the same chemical element. Now, units of radioactivity. The SI unit of radioactivity is becquerel, named in honor of scientist Henry Becquerel. 1 becquerel is defined as 1 transformation per second. An older unit of radioactivity is curie. 1 curie is equal to 3.7 into 10 raised power 10 becquerel. Now, half-life. The decay of radioisotopes is commonly expressed by its half-life, that is the time necessary for 1/2 of the radioactive sample to decay. The relationship between half-life and decay constant can be demonstrated as T half is equal to ln 2 by lambda. The factor of ln 2 is natural logarithm of 2 and is equal to 0.639. Now, half-life in biology and pharmacology. A biological half-life or elimination half-life is the time it takes for a substance, drug, or a radioactive nuclide to lose 1/2 of its pharmacologic, physiologic, or radiological activity. In a medical context, the half-life may also describe the time that it takes for the concentration of a substance in blood plasma to reach 1/2 its steady-state value. The relationship between the biological and plasma half-lives of the substance can be complex due to factors including accumulation in tissue, active metabolites, and receptor interactions. With this, we come to the conclusion of our lecture. Thanks for watching. Have a nice day.